In this video, we're going to talk about what a dot product is. So there are two ways to multiply vectors. The first is the dot product. So the dot product. And that is what we're talking about in this section, section 12.3. And the second is the cross product. The cross product we will talk about in the next section, 12.4. So cross product section 12.4. All right, so I'm going to begin by defining the dot product algebraically. So I want to give an algebraic representation of the dot product. Okay, so here is the definition. So the dot product, and sometimes we call this the scalar product or the inner product of two vectors. So u is written in terms of its components, u1 I hat plus u2 j hat plus u3 k hat, and v, which is written in terms of its components, v1 I hat plus v2 j hat plus v3 k hat, is u dot v. So that's the notation for the dot product. I just wrote a dot in between two vectors. And what it's defined to be equal to, so I'm going to use my symbol for defined to be equal to, which is an equal sign with a colon. All right, and what it's defined to be equal to is you multiply the I components together, u1, v1, plus, and then you multiply the j components together, u2, v2, plus, and then you multiply the k components together, u3, v3. So in terms of the computation, what we're doing is we multiply component by component. So we multiply the I components together and then the j components together, and then sum, and then add those values up. So this would work even if we were working with vectors in two-dimensional space and they just had two of these components, an I component and a j component. Except there we would just be summing two things instead of three things like we are here. It also works in higher dimensions. Okay, so the other comment that I want to make about this is, so what we are sort of inputting into the dot product is two vectors. So the input is two vectors. And the output is what we have here. The output, notice, is no longer a vector. The output is a scalar. So when we multiply all those components together and then sum them, that's just a scalar. It's just going to be a number. Okay, so we have this algebraic definition of the dot product, and we will do an example actually taking the dot product of two vectors later in the video. But I want to answer, I think, a more important question first, which is, what does this definition mean visually or geometrically? Okay, so I need to talk about the geometric representation of the dot product now. Okay, so let's draw a picture. So in this picture, I'm going to have a vector u. So a vector u, and then a vector v. And then let's say that, so I've drawn them so that their tails start at the same point. Okay, and I'm going to say that this angle is some angle theta. So now I'm going to draw one more vector, a vector that connects the head of u to the head of v like this. And this vector is v minus u. So if we think about that, if we use our sort of head to tail method of adding vectors, if we take the vector u and then we add that to v minus u, so if we take u and we add that to v minus u, we would expect to get the vector that we have here, just starting at this point and ending at that point, which is v. And sure enough, if we add these, the u's cancel and we get v. Okay, so that orange vector that I had drawn in is v minus u. So now let's write all of these vectors in terms of their components. So let's say that u in component form, this is u1 and then u2, u3. I'm just writing in component form. And v would be v1, comma v2, comma v3 in component form. So subtracting the two vectors, we subtract them component by component. So it would be v1 minus u1 for the first component, v2 minus u2 for the next, and v3 minus u3 for the last. Okay, so I have this picture. So I have vectors representing each of the sides of this triangle. So what we will do with this triangle is use the law of cosines. So the law of cosines. So some trig is showing up here. Okay, so what does the law of cosines say? So the law of cosines, I'm going to draw a general picture of a triangle. So let's say I have a triangle, and I call this side A, and this side B, and this side C, and this angle between A and B theta. The law of cosine says that c squared equals a squared plus b squared minus, so it's looking kind of Pythagorean-esque, except there's one extra term, minus 2ab cosine theta. And that's the law of cosines. Okay, so I'm going to zoom out a little bit, and I want to make a note before we proceed with this computation. So the note is, in the law of cosines, when theta is pi over 2, so that means 90 degrees, which is a right angle. When theta is pi over 2, this cosine theta becomes 0, and we end up with the Pythagorean theorem. This becomes the Pythagorean theorem, which means the law of cosines is a generalization of the Pythagorean theorem. So the law of cosines is a generalization of the Pythagorean theorem that applies to any triangle, so not just a right-angled triangle. Okay, so what happens if we use the law of cosines on our vectors here? Okay, so I'm going to try to keep it zoomed out a little bit so I can still see them. Okay, so using the law of cosines, so I'm going to say that C is the v minus u. So if we take the length of v minus u and we square that, the law of cosine says that should be equal to the length of u squared plus the length of v squared minus 2 times the length of u times the length of v times cosine of theta. All right, so now let's evaluate these lengths, because we know how to figure out the length of a vector. We talked about that in the previous section. Okay, so when we take the magnitude or the length of a vector, we'd end up with a big square root, but then when we square it, that's going to get rid of that square root in order to leave us with what's inside the square root. Okay, so when we take the length of v minus u, we have to take each of its components and square it. So the first component is v1 minus u1. I'd have to square that, add that to the next component squared, v2 minus u2 squared, add that to the next component squared, v3 minus u3 squared. And again, usually I would square root this, but the fact that I have the squared on the whole thing means the square root will get canceled away. All right, so now on the other side, the length of u squared would be, so I'll take the components of u and square them and sum that. So u1 squared plus u2 squared plus u3 squared, and the squared would cancel that square root. Similarly, the length of v squared is going to be v1 squared plus v2 squared plus v3 squared, oops, sorry, not cubed, squared. And let's keep the last term as it is. So the minus 2 length of u times the length of v cosine of theta. All right, so the next thing I'm going to do is, with these terms on the left, these orange terms, where I have v1 minus u1 squared and so on, I'm going to expand them. So let's do that next. I'm running out of room, so I'm going to move it to the top of the page. All right, so I've gone ahead and first I just copied down. So this first line is just the same line that I had before. Then in the next step, I went ahead and expanded the left-hand side. So for example, v1 minus u1 squared, so v1 minus u1 squared is v1 squared minus 2v1 u1 plus u1 squared. So I've expanded everything. And then the equal sign I wrote here just because there's so many terms now that I need to split this up over two lines. So if we simplify this, a bunch of terms cancel on the left and the right-hand side. For example, this v1 squared cancels with that v1 squared. And in fact, all of the squared terms on both sides cancel. And after we cancel them, what I'll end up with is I can factor out the negative 2 from the left-hand side and be left with u1 v1 plus u2 v2 plus u3 v3 on the left-hand side. On the right-hand side, after we cancel, we will just be left with this term, because all the squareds will cancel. So we'll be left with minus 2 times the length of u times the length of v times cosine theta. And now I could divide both sides by negative 2. But notice that this thing in parentheses looks familiar. u1 v1 plus u2 v2 plus u3 v3. This was the dot product. This was our definition of u dotted with v. So now if we divide both sides by the negative 2, what we get is that u dot v equals the length of u times the length of v times the cosine of theta, where theta was, in fact, let me write this down, where theta is the angle between them, u and v, and we're going to think of theta as being an angle between 0 and pi. So theta is the angle between our two vectors, u and v. All right, so I'm going to draw a picture one more time. So in the picture, we will have a vector u and a vector v, and I'm drawing them emanating from the same point, and then theta is the angle in between them. So visually, what this formula that we've now derived says is the dot product is equal to the length of the first vector, u, times the length of the second vector, v, times the cosine of the angle in between them. So there's a geometric interpretation for the dot product involving the lengths of the vectors and involving the angle in between them. Okay, so now that I've highlighted this formula, I forget, I'm not sure if I highlighted my first formula, the one with just the multiplication. Yeah, let's go ahead and highlight this one as well. So we have these two formulas for the dot product. This first one, the one that I'm highlighting now, was an algebraic formula, and we'll do an example in just a minute or two using this, in fact using both of them. And this formula was more of a geometric formula involving the lengths of the vectors and the angle in between them. Okay, so next I want to introduce some notation, and then after that do an example. Okay, so there is some notation that we can use to talk about vectors that have a certain number of components. So to lead up to this, let's recall that when we write this R, capital R symbol, with another line vertically here, this is the symbol for the real numbers. But in multivariable calculus, we'll commonly see this notation where we have like R, and then there's a number in the exponent. You also see this very commonly in linear algebra and a bunch of upper division math. Okay, So R2 refers to all real valued vectors with two components. So for example, the vector 3, negative 1 is a vector with two components. So we would say this is an element of, that's what that symbol stands for. It's an element of R2. It's one of the vectors that has two components, and what real valued means is each of the entries is a real number. So similarly, R3 would be all real valued vectors with, let's put this in blue now, three components. With three components. So in the dot product formula that I wrote here, this U and this V, they were elements of R3 because they each had three components. But I could have defined this in terms of vectors with any number of components. I could do two components, one component. I could do higher dimensions. Okay, so let's go back to our notational comment. Okay, so in general, if we have Rn, that is all real valued vectors with n components. So for example, if we had the vector 1, 1, 2, 3, 5, this vector is 5 components, which are real numbers, so this is an element of R5. Okay, and then I want to note two things. In 2 dimensions, R2, and 3 dimensions, R3, the dot product has that nice visual representation. U dotted with V will be equal to the length of U times the length of V times the cosine of the angle in between. And we could derive that even in 2 dimensions using the law of cosines. In fact, it's actually a little bit quicker computationally in 2 dimensions. In higher dimensions, we can't really visualize the angle between 2 vectors. In fact, we can't even visualize 2 vectors in higher than 3 dimensions. So in higher than 3 dimensions, this formula, so this formula right here, is actually what's used to define an angle between 2 vectors. Because we can, in higher dimensions, we can still take the dot product of 2 vectors using that formula, using the algebraic formula over here, even in higher dimensions. And we could take the length of 2 vectors, like the length of U and the length of V, and if we isolate for cosine of theta, we can define what theta would be in higher dimensions. All right, so let's look at an example. All right, so let's let A be, so we have these 3 vectors, A, B, and C. First, let's find the angle between the vectors A and B. All right, so because it's talking about finding the angle between 2 vectors, I'm going to use my geometric formula for the dot product. So recall that was A dotted with B equals the length of the vector A times the length of the vector B times cosine of the angle in between. Okay, so on the left-hand side, to take the dot product of A and B, let's use our algebraic definition of the dot product. So first we multiply their I components together, so that would be 2 times the 6. Added to, multiply their j components together, that's negative 1 times 2. Added to their k components multiplied, that would be 2 times negative 5. And this is going to be equal to the length of A times the length of B times cosine of theta. I noticed that the left-hand side is going to simplify really nicely, which is why I haven't started to compute the length of A or the length of B. It'll turn out we don't need to. The left-hand side is actually 0. So we get 0 equals the length of A times the length of B times cosine of theta. And notice that both A and B, both of these lengths are definitely not going to be 0. because the only vector that has a length of 0 is the 0 vector. Any other vector is not going to have a length that's just 0. Okay, so if both of those are not 0, and this whole thing equals 0, that must mean that cosine of theta equals 0. That's the only way for this to be true. And if cosine of theta equals 0, that means theta is pi over 2. So theta is pi over 2. That is actually the angle in between these two vectors, a and b. All right, so what I want to do is I want to do a demo using a website called Geogebra. So Geogebra demo at this point, to show what these vectors look like in a 3D graph. All right, so this is what Geogebra looks like, and I've gone ahead and inputted two vectors right here, but I've only shaded in one of them. In fact, right now none of them is shaded, and here's the first vector, a. So I've gone ahead and entered in the components of this vector. So this red axis is the x-axis here. The green one is the y-axis. This is the positive direction. And this bluish purplish one, I guess maybe more purplish, is the z-axis. So going up is the positive z-axis. So notice that if I look at this from above, with the vector that I have, I can see that it is going sort of 2 in the x direction. And then this is the negative y direction, negative 1 in the y direction. And that makes sense. And the z component is 2, so if I tilt my graph a little bit, I just have to click on it and tilt it. If I tilt it so that the xy plane looks flat, I can see that it's kind of going up a distance of 2 in the z direction. And that's good. That's what it should be doing. Okay. Sorry, it's just like lagging a little bit while I'm recording with this. Okay, but now let's go ahead and draw on that other vector. So what I want to do is hopefully convince you that they make a right angle, because the angle between them is pi over 2. If I just tilt it a little bit to the side, I can see that, yeah, it looks like they do make a 90-degree angle or a right angle. Okay, cool. So I think Geogebra it's a pretty good website in that it lets me draw certain 3D things like this, like vectors, and it's helpful to visualize. All right, so now let's return to the notes. All right, so one key thing that happened here was the dot product of two vectors ended up giving us 0. And when that happens, as we saw, that means those two vectors had an angle of pi over 2 in between them, or 90 degrees, which means they're perpendicular. So that's what I want to define next. We say that two vectors, u and v, in Rn are orthogonal. Orthogonal is a more sort of universal term for perpendicular. So orthogonal, which means the same thing as perpendicular. There's actually another word that we're going to see later in our class to refer to perpendicular or orthogonal, which is normal, if their dot product is 0, just like we saw here. Because when their dot product is 0, that's going to mean that cosine of theta is 0, assuming that neither of the vectors is the 0 vector. And that's going to lead to the angle in between being 90 degrees. All right, so now let's do another problem like this. So now let's find the angle in between A and C. So if I want to find the angle in between A and C, I want to use the same general idea. I want to use my dot product formula, but this time with A and C. So use the fact that A dotted with C would be the length of A times the length of C times the cosine of the angle in between these two vectors. Okay, so let me zoom it out a little bit so I can just see all my vectors and start to take these dot products. So on the left-hand side, when I dot A with C, let's first multiply their I components. So it's 2 from the A and then 1 from the C. Okay, and then dot their J components. So, okay, so added to -1 from the from vector A times 3 from vector C. And then their K components, which would be 2 from the A, and then 0, because C does not have a K component, so it's 0. Okay, so that's the left-hand side. On the right-hand side, if I want the length of A, this time I'm actually going to work it out, because the dot product on the left isn't 0. So let's actually work out these lengths. So I would get 2 squared, basically I have to square all their components, add them up. So 2 squared plus negative 1 squared plus 2 squared, and then square root that thing. We've seen this before. That's how I get the length of a vector. And then the length of C would be 1 squared plus 3 squared plus 0 squared. And then that whole thing is being multiplied by cosine of theta. All right, so now let's continue to simplify this. So the left-hand side becomes negative 1. And on the right, we end up with root 9 times root 10. Okay, so I'm running out of room. Let's go to the next page. Okay, so we had negative 1 on the left. And on the right, we had root 9 times root 10 times cosine of theta. And isolating for cosine of theta, we get negative 1 over 3 root 10 equals cosine of theta. So to get theta, I need to take inverse cosine. So theta would be inverse cosine of negative 1 over 3 root 10. Because the inverse function would switch the input and the output. So instead of theta being the input, as it is for cosine, it's going to be the output of cosine inverse. And the output of the cosine equation was this fraction, negative 1 over 3 root 10, and that's going to be the input of cosine inverse. So if I plug this into a calculator, this is about 1.676. At least that's what it'll tell me we have in radian mode. Okay, so using a calculator, that's our angle in radians, and if we convert this to degrees, this is 96.05 degrees. And that's our angle. That's the angle between the vectors A and C. This is how we would work it out if the dot product wasn't 0 and they weren't just perpendicular or orthogonal. All right, so in terms of our goals, we have defined the dot product algebraically and then connected that to the geometric interpretation of what it is.